Okay, sorry, interrupted a little bit. So we have 2 points on the indifference curve. We have point A. Come on, man. Come on, point A. Jeez Louise. Okay, so there's point A. Okay, now we want point B. So point B is going to be here. Okay. Point A is going to be this red one over here. Okay. So point A let's say is 5 not pizzas and 1 pizza, and point B is 5, so 1 not, no, let's say 2 not pizzas and 5 pizzas. Okay. What is the utility you get from 5 not pizzas? From 5 and let's say not pizza and no, sorry. So 1 pizza, 5 not pizzas. Well, the utility is equal to 1. And the utility from 5 pizza, 2 not pizza, what's that? It's also equal to 1. Okay. How do I know that? Well, because they're both on the utility function, or sorry, the indifference curve that corresponds to a utility of 1. Okay. So if I give you an indifference curve, I have it labeled, and I give you a point on the indifference curve, you should know what the utility is based on what the utility for that indifference curve is. You should also know that the utility for this person so this consumer is indifferent between the consumption bundles represented by five pizza, 2 not pizza, and 1 pizza, 5 not pizza. Okay. All right, so we know that they that all points on that same indifference curve correspond to consumption bundles that yield utility equal 1. Another way of saying that is all points on that indifference curve the consumer is indifferent about. Okay. And then one last point is if I connect a line between A and B, okay, let's undo that because that was gross. Let's do a line between, I'm just going to redraw something. So if I do 5 consumption bundle, and it's still going to be pizza and not pizza. So everything that's not pizza is still on the x-axis. Okay. We have, let's call this C and let's call this D. And if I draw a line between C and D, okay, let's call it E. So everything on the orange line everything on the orange line is some mix between C and D. So less pizza than in D, but more not pizza than D, or more pizza, I shouldn't say or, it's and more pizza than C, but less not pizza than D, okay? So basically what I'm saying is E is some sort of mix between pizza and not pizza that is better than C for pizza, but worse than not pizza, better than D for not pizza, worse than D for pizza, okay? AKA E, so what I'm going to say is E is a more balanced consumption bundle. Notice that E is northeast of the northeast of the indifference curve, i.e. E is on a higher indifference curve, i.e. that is, E has more utility than C and D, okay? By the shape alone, by having an indifference curve shaped like this, like a skateboard ramp, basically. Okay, convex preferences, we call it. We are saying that we prefer a mix relative to a lot of one thing. Okay. This is a particular example of an indifference curve. It doesn't have to be a real-world indifference curve. You might have different preferences. For instance, today, or not just today, but when I get the meals at Popeyes, I don't care about the mac and cheese or the mashed potatoes or the biscuits. I want the chicken. All right. So I would rather eat a lot of chicken and have none of the additional fixins than substitute stomach space in order to get the fixins. Okay. But that's me. And chicken is my favorite food, so whatever. But in general, most people probably prefer the mix between normal things and not normal things. Okay. And even if I like a lot of chicken, it's not that every day I'm going to be eating, a bucket of fried chicken every day, right? I'll consume everything that's not chicken every once in a while, right? So in general, people tend to prefer the mix. And I'm not saying that this is that convex preferences are an assumption economists always make, but it tends to follow from diminishing marginal utility. So it's a pretty standard assumption as well. So just regarding that last point, because the more pizza I consume, the lower the marginal utility of the pizza is. At some point when I'm consuming a lot of pizza, I'm going to have a high marginal utility for consuming even a small amount of not pizza. So I'm going to want to start moving towards not pizza. Okay. But, at the end of the day, economists can make all the assumptions about preferences that they can. Real world preferences are going to be what they are. So, you're going to have to you're going to have to see what consumers are actually consuming before you can work on that market. And sometimes I think when economists make assumptions about a particular market and the preferences aren't very clear, they're going to get called out on that. Okay. Okay, so once again, the indifference curve is the meaning of an indifference curve is all the possible consumption bundles that correspond to one utility level. Okay, the shape of an indifference curve is usually convex. The reason it's convex is because there's usually a trade-off between goods where at some level I want more not pizza than pizza. So if I'm consuming a lot of pizza, eventually I'm going to want a little bit more not pizza. So I tend to prefer some sort of mix between pizza and things that aren't pizza. So that's why indifference curves tend to be convex, but they're not always. And again, that follows from the law of diminishing marginal utility, okay, which is an assumption, it's not an iron law, but it's a pretty good assumption and a pretty good foundation for making your decision about most markets. Okay. And then the last point is that just that indifference curves if you like both goods, tend to have higher utility as you go further away from the origin. But if you don't like both goods, that's not always going to be the case. Okay, or that's not that it's not always going to be the case. If you don't like both goods, it's not going to be the case. Okay. All right. Review part 2. So next up, I want to talk about budget constraints. So budget constraint is basically if I have pizza, it costs me $2 a slice, and not pizza costs me $5 per not pizza. I don't know the unit of not pizzas. And I have $200 in income for that week. Then my per week budget constraint is 200 equals $2 times pizza plus $5 times not pizza. Okay, and I can map this. Okay, so at most I can consume 100 pizzas. And at most I consume 20 not pizzas. So that's my budget constraint, okay? Where the slope of the budget constraint is going to be rise of 20, negative 20 divided by 100, which would be the run. So negative, I'm sorry, this should be 40. Did something wrong. Okay, and you get the intercepts by just seeing how much of the maximum amount of not pizza I can consume and what's the maximum amount of pizza I can consume, aka setting not pizza to 0, dividing by 2, I get 100 pizzas. Setting pizza to 0, dividing by 5, I get 40 not pizzas. Okay. So the slope is going to be a run of 100 and a rise of negative 40, so you get negative 2/5, aka negative price 1 divided by price 2, or let's say negative price of X divided by price of Y. Okay, so that's the slope of the budget constraint in general. Okay, and a budget constraint in general is going to be your income is equal to P of X times X plus P of Y times Y. So the price of good X times X plus the price of good Y times the quantity of Y. Okay. So if you were to put this into slope-intercept form, basically we want y on one side, so py times y equals px times x minus I. Okay, and then we're going to get y equals px divided by py times x minus I divided by py. So your slope equals px divided by py, and your intercept equals negative. Sorry, I did something wrong. Oh, I'm moving the wrong thing here. What did I do wrong? So, oh, right. So I should have subtracted. This from both sides, not this. Okay, so this should be negative, and this should be positive. So your intercept, so your slope should be the negative price ratio. Your intercept should be I divided by py. All right. So that's your budget constraint. It's just all possible consumption bundles that you're capable of consuming will be under the budget constraint. So everything in red and black is feasible. Okay. All right. I'm just going to write budget constraint at the header so that if you guys are just looking at the notes, you can see this. Budget constraint. All right. And then the next point I want to make is your marginal rate of substitution. And basically that's how much of one good you'd be willing to give up in order to get another good that will keep you at the same utility level. So for a fixed utility level, how many samosas do you need to trade off to get the same utility how many samosas do you need to trade off in order to get, or to get rid of, in order to get, one more time. What is the amount of samosas you need to give up and the amount of beers you need to get in return in order to stay at the utility level? That is your marginal rate of substitution. How many samosas do you substitute for beer, or how many beers do you substitute for samosas in order to get the same utility level? Okay. So your marginal rate of substitution of beers and samosas will be your marginal utility of beers divided by your marginal utility of samosas. Okay. So the understanding is if your marginal rate of substitution is equal to, let's say, Z, that means you're willing to give up Z samosas in order to get one more beer. Okay. So basically, how many samosas do I give up to get one more beer is going to be your marginal utility of beer divided by your marginal utility of samosas. Okay. And I get confused by this, what's on the numerator, what's on the denominator, how to interpret that. And I know that it's like an easy thing to mess up. So let's think about it this way. Okay. This is the easiest way, I think, to think about it. So MU, let's say your MU beer equals X, your MU samosas equals Y. So your marginal rate of substitution for beers samosas is going to be X over Y, right? If I really need a beer, right, X divided by Y is going to be really high, right? Okay, so if X divided by Y is high, that means that X X is much larger than Y, right? AKA marginal utility of beer is higher than my marginal utility of samosas, okay? Which means I haven't consumed a lot of beers, but I have a lot of samosas, okay? So I'm really willing to give up a lot of samosas in order to get back some beer. Okay. So remember, marginal utility is going to be decreasing. Mu decreases as consumption. Let's say MUX decreases as X increases. Same thing with Y. Right? So the higher my marginal utility, the less of X I'm consuming, essentially. So if I have a high marginal rate of substitution, what that's telling me is I really need a good X. Okay? So if I have a high marginal rate of substitution of beers for samosas, that means I'd be willing to give up a lot of samosas in order to get one beer. Okay? That's the intuitive way to think about it. Okay? If I have a high MRS, that means I'm MRS for beers and samosas. That means I'm willing to give up a lot of samosas for one beer, aka so just to put this all in one nice little neat bow, aka MUX is high and MUY is low. MU beer. Not MU Samoas, MU samosas. Okay. All right. So your marginal rate of substitution is basically the rate of your marginal utilities. Marginal utility decreases as you consume more of that particular good. So the higher your marginal utility, the more you want that particular good, the more that particular good will increase your utility of just consuming that one extra piece. So the higher marginal rate of substitution, the more you're willing to trade the denominator good for the numerator good. Okay. All right. So at the optimal consumption bundle, why am I doing that? And what I mean by optimal consumption bundle, just the best mix of beers and samosas, or pizza and not pizza. So pizza, you know what? Let's do this. And now let's start again. Sorry. I lied. It's just easier to restart. All right, so on the X we have pizza, On the y, we have not pizza. It doesn't matter which good goes on which axis unless I tell you which one I want on which axis for the sake of grading. But it doesn't really matter. There's no like set in stone rule. Okay, and I have, let's say, an indifference curve. I'm going to make it orange. And this utility equals x. Okay. And I have a second indifference curve, and that utility equals y. Okay. And then I have a budget constraint. Okay. That's my budget constraint. All right. So at the optimal point, at the optimal consumption point, the indifference curve is tangent to the budget constraint. All right. So what does it mean to be tangent? It means to be touching at only one point. Let's do some black. So at the optimal point, the budget constraint is tangent to the indifference curve, or the indifference curve is tangent to the budget constraint. Okay. So right now I have 3 points at which the budget constraint touches an indifference curve, but I also have to keep in mind there's going to be a million mini indifference curves in between here. It's just the two that I happen to draw. But the budget constraint is going to be, for what's visible, the budget constraint is touching at point A, point B, and point C. Okay. So BC touches ICs. I'm just going to write visible ICs at A, B, and C. Okay. So BC for budget constraint, ICs for indifference curve. At A and C, utility equals X, and at B, utility equals Y. I like both pizza and not pizza, so I can say that Y is greater than X, aka B is on a higher indifference curve, aka utility of B is greater than utility of A, which is equal to utility of C. Okay. So I prefer B to A and C. Okay. They're all those things are saying the same thing. Okay. You can also say that B is a less extreme consumption bundle than A and C. And that by that I just mean that the same thing, I'm just talking about the same thing that I drew up here, right, with E, C, and D. I'm actually going to get rid of that part though, because it's not really necessary for what we're saying. All right. So I prefer B to A and C. And B is the only point that touches the budget constraint on that indifference curve. Okay, so it is tangent is another way of saying that. If it weren't, then you'd have 2 points cutting through like A and C, or like if we drew another line here, we could say it's like point D and point E. But B is tangent. So B is on the highest possible indifference curve that it still is feasible, aka it's still on the budget. Okay? So at the optimal consumption bundle B, at optimal consumption bundle, or the optimal consumption bundle should only touch the indifference curve. I'm sorry. The optimal consumption bundle B should only touch the indifferent. At the optimal consumption bundle B, the budget constraint should only touch the indifference curve at one point. Okay. Otherwise, I could go higher. I could go to a higher indifference curve. Okay. Just like I did going from X to Y. Right? So that's what it means to be tangent. AKA BC is tangent to IC. Okay. And then there's just one small other point I want to make. So the indifference curve is fixed utility, right? So I'm fixing utility, and it captures the trade-off for the x-axis good of the y-axis good, right? So for a given utility, what's the slope of the indifference curve for a given utility? The slope of the indifference curve gives how much y I have to give up in order to stay at to substitute for x in order to be on the same utility. Okay. So if I'm moving from here to here, and I take the rise over run, so if I'm moving from, oh, sorry, I don't want that. So the rise over run from E to B is the amount of E I have to give, the amount of not pizza I have to give up to get, give up in exchange for pizza to get the same utility. And what does that sound like to you? Another way of saying that is AKA the slope of the indifference curve is the marginal rate of substitution. Okay? So it's the amount of not pizza I have to give up in order to get a pizza. What's that? That's the marginal rate of substitution for pizza, not pizza. Okay? And what did I say about the slope of the budget constraint? Slope of the budget constraint Well, we found that earlier, right? It's going to be negative px divided by py. Right, that's up here. Sorry, I moved up and I didn't point to it. That's right here. The slope of the budget constraint is negative px divided by py. So the tangent to the indifference curve is going to be the slope of the indifference curve at optimal consumption bundle which is the marginal rate of substitution. And then we can say the tangent to the indifference curve is equal to the budget constraint at optimal consumption bundle. Right, that's what we just did right here. So this one comes from the definition of what it means to be tangent. Right, it's the slope of the indifference curve. And then this one comes from the exercise that we just did, where we demonstrated that the indifference curve has to be tangent to the budget constraint. So we can say for sure at optimal bundle, slope of the IC equals slope of the budget constraint, okay, at optimal bundle negative px divided by py. Sorry, I got it backwards. Mux divided by mu y equals negative px divided by py. Okay. I think there should be negative in front of it. Nope. Okay. So the optimal consumption bundle has a few different rules, or a few different ways of expressing itself. So at the optimal consumption bundle, your indifference curve is tangent to the budget constraint. That's like the graphical way of showing it. Alternatively, you can say the marginal rate of substitution is equal to the slope of your budget constraint. Okay. Every time I just need to restart this at one day. Okay, so at the marginal rate of substitution, or sorry, at the indifference curve, if you drew a tangent, you get the marginal rate of substitution as your slope. Okay, it's also equal to the slope of your budget constraint. Okay, and then another way of writing that is, nope, where is it? Your margin utility of beers divided by your margin utility of samosas, right? This is your marginal rate of substitution. It's equal to the price of beers divided by the price of samosas. And you exhaust your budget constraint. Okay. Because it could be tangent, or sorry, you can have the indifference curve match the slope of the budget constraint. Like you can have a tangent here that has the same slope as the budget constraint, like it's parallel, but you're not exhausting the whole budget, so that's the second rule you need. Okay. Another way of writing this is margin utility of beers divided by price of beers equals margin utility of samosas divided by price of samosas. Okay. They're all different ways of saying the same thing, and you can see it with simple division. Okay. Just rearranging the terms here. All right. I think that's it for the review. So let's move on to the new material.